Hi, everyone. Thank you so much for coming. I really appreciate, the CCA being given this opportunity to host this workshop at a very critical time in the development of the LSST project. Um, I in preparation for this, I was really kind of thinking about. I was around at Sloan Foundational Institutions at the start of Sloan, so before it was online, and people were wondering, is it going to work? And the people close to the project kind of understood that it was going to be profoundly important, but also different. In SQL, nobody knew what SQL was unless they were like a student of Alex Soleil's, like Andy. And so there was this people close to it knew there were going to be changes, and nobody understood any of that at that time, kind of out in the hinterlands. But people in the project knew that science was going to be done differently once this came online. And I think LSST is at a very similar stage in its development that I think people still imagine they're going to download bits files. If you're about my generation, you hope it's going to be downloading like ASCII files. And if you're a little younger, maybe a FITS table. And if you're younger than that, like HDF5. But I think the whole concept of how LSST has to operate is really going to sort of shake a lot of the field to its core. And so this is an opportunity that you guys have to figure out how does that function in practice, because I think people's understanding of the ways that you can work with data and information is going to be very different 5 to 10 years from now than it is today. I think people in this room know something about that, but I think the majority of people out there really do not yet fully understand the ways in which things are going to become different because of this project. So what you guys are doing here is very, very important. At CCA, we're just honored to be in any way a part of it. And so for those of you tied up with the Link project, congratulations. This is really, you guys are doing something that really, really matters, I think, to the future of the field. In terms of the CCA itself, the CCA is a very flexible organization. One of the things that is not flexible about is thou shalt not have food or drink in the auditorium. Like, they're really profoundly serious about this. Logistically, while you're in the auditorium, if you have questions, there are seat mics next to you. There's like a little button. So press the button so that people who are remote can hear. And the people in the AV people will speak out like the voice of God if you don't. So the breaks will be out here. There's usually food and drink that you cannot bring back into the auditorium. And I believe Adrian, Katie, can you think of anything else local? I would say the other thing is, we are locally, the case rates for COVID are low. They are starting, in an absolute sense, they're low. The gradient isn't that great, but it's particularly not great if you're not vaccinated. And, the CCA, everybody who comes into the building has a vaccine requirement. But if you are out in public, you may not be in such a situation. So just, use prudence as you're going about to dinner. Please respect everybody's personal decisions about where they are in terms of their level of personal safety. Everybody is dealing, everybody's carrying a different load. And so just be respectful of other people. So I think that's it. Looking forward to a really great workshop.
Thanks, Julianne. Perfect, thank you. I'm going to take my mask off. It's kind of still a strange experience. Welcome. This is the first in-person astronomy meeting I've been to in 2 years and 3 months. And so it is very exciting. It's exciting to be here, to be able to talk about, just to talk in person. It's exciting to be able to talk about LSST science, and it's particularly exciting to be able to, coming from Seattle, to be able to not just be able to jaywalk, but to be actively encouraged to jaywalk in New York. So my name's Andy Connolly. I am a professor at the University of Washington. I'm the PI from the University of Washington side for Link Frameworks. And I, together with Rachel Mandelbaum, who is a professor at Carnegie Mellon, who is also the PI for the Carnegie Mellon side of it, what we wanted to do is to give you an introduction to the meeting, why we're holding it, and also to link frameworks, which is the project that is trying to allow us to go from data to science via software. So before we get into the details of this, there's a couple of logistics I just want to talk about. We will be following the Flatiron Code of Conduct. If you haven't read it, I would encourage you during my talk to actually go to this link and read through the Code of Conduct. As part of LINC, we are committed to respectful, collaborative exchanges. It is important that everybody has a voice in terms of discussing the science that we're going to be doing, and that all of our voices are heard, so that we actually have an inclusive way of actually approaching the science. And this is one of the the core values of LINC that we established early on with the foundation of the project. The second just logistical thing is to introduce Alison Rose, who is going to be doing some filming here. And I'll just give Alison a couple of minutes just to give you an overview of what she's doing.
Hi, everyone. As Andy said, my name is Alison Rose. I'm a documentary filmmaker based in Canada, in Toronto. I have a long-standing practice of making films about astronomers. And you can see clips of my earlier films on my website, and I can share that with you. My intention here, my wish here, is to document people having conversations about work they'd like to do and the problems that it poses for them. I want to share with the general public the process of doing science, to show that it's about relationships and friendships and conversations, and to allow people to follow the process toward learning and making discoveries. If you don't want to be filmed, it's fine with me. Please put a sticker on your name, on your badge, and that way, when we're editing, I see that sticker and I know we'll just cut around you. I welcome your questions, and I look forward to listening to you work this week. It's a privilege to be here, and I look forward to meeting you.
Thank you, Alison. And the stickers are available at the front desk if anyone didn't pick one up and they want to put it on their badge. So what we're going to do here is, first I'm going to tell you a little bit about LINC and the LINC project, and then Rachel is going to talk about the meeting, our objectives, and how we're trying to structure this meeting. So what LINC stands for is the LSST Interdisciplinary Network for Collaboration and Computing, which is why we only refer to it as LINC going forward. LINC is an LSST initiative. Originally, it started out as a collaboration between the University of Arizona, Carnegie Mellon University, Northwestern University, and the University of Washington. But the goal behind LINC is to develop programs that can help us prepare and support the science that's going to come out of the LSST. So just to give you some examples of the programs that have started up recently, LINC Frameworks, which is a program to develop software infrastructure, is what we're talking about at this meeting here. There is a Catalyst Fellowship Program, which is a prize postdoctoral fellowships, which I believe were just announced a few days ago, the first cohort of those prize fellowships. There is the long-standing LSSTC Data Science Fellowship Program, which is a graduate training program to prepare graduate students to work with LSST data. And that has been run for many years out of Northwestern University. And we hope over the next couple of years that we'll have more programs to actually announce to support LSST science. The one that we're particularly interested in today is called LINC Frameworks. LINC Frameworks is the goal of LINC Frameworks is to develop software systems that allow us to do science with LSST. So why do we care about that? Well, we care about that because we know that Rubin is going to be taking observations of the sky. Any part on the sky will be observed 1,000 times over 10 years. We know that the camera from Rubin that you see in the second picture will cover the ultraviolet through to the near infrared, U, G, R, I, Z, and Y. The This will generate these both sequences of images, and once we co-add these, some of the deepest wide field surveys of the sky ever undertaken. The Rubin data management science pipelines will be taking those data, they will be calibrating the data, and they will be applying state-of-the-art algorithms to detect the 37 billion stars and galaxies, to identify their positions, to understand the characteristics, measure the properties, and then place them into the Rubin science platform, where both the images, the calibrated images, and the catalogs will be made available to the community as a whole. So through Rubin, we will have access to this incredible astronomical resource, 1,000 times the size of SDSS, with the expectation it will have the same impact on science as SDSS had, as Julianne was referring to a couple of decades ago. So what we're doing with the frameworks is to try to take it from the data to develop software to enable the science. So you can think about this as, how do we enhance the Rubin science platform to enable science at scale? And so what this means to be able to produce science at scale means we will be having to develop new algorithms. It means we'll have to take user code from existing users. We have to be able to bring that together with astronomical software projects such as AstroPy and enable those to work at the scale and the complexity of the Rubin data. And to do this means bringing in astronomical code bases together with industry standard software tools such as Spark or Dask that allows you to distribute your workload over thousands of computers, or through to things like Kafka that deals with the streaming of data, streaming of events. And it's by bringing these tools that already work in industry, that works at scales much larger than we're even going to achieve with Rubin, and coupling that together with the astronomical codes, we hope to be able to provide an enhancement to the Rubin science platforms to allow us to do science at scale. And that's what Link Frameworks wants to enable. So to make this happen, we are building up a team of about 14 people. It will be on the order of 5 research scientists who will be computationally literate astronomers, and about 9 software engineers. And these could be from academia, they could be industry, but coming with experience with cloud computing, with high performance and high performance computing. And the idea behind that is to bring these software engineering to start helping us build the software infrastructure that allows us to run our algorithms. That could be anything from, you've come up with a new algorithm that allows you to detect counterparts to Boyajian star, some unusually varying star. And now you want to run that across the size of the LSST data set. You have your own algorithm for how to measure photometric redshifts that's targeting very high redshift galaxies, how to build and train that and deploy that so that you can share that to build up catalogs of high redshift galaxies. I won't ask the people to stand up in the audience, but there are a number of people who are either part of Link now or will be part of Link in the fall. I will just leave these names here for a second. I'll encourage you to reach out to them, to talk about Link, to talk about your science cases, and to learn more about what we're trying to do. But the way we can actually think about Link is what we're trying to do is to enable end-to-end analyses, science analyses. We're trying to bring in software engineering so that these projects are both scalable, but also reproducible and usable for the average user. So this means that we're not trying to turn everyone into software engineers. We're trying to make it so that your science can be done at scale. To do this, we are running workshops like this, where we come together to understand what are the commonalities in terms of the science cases we're interested in, and how does that translate into the software. We will be running incubator projects once the software starts coming out. So that allows you to come in and work with the software engineering team to ensure that your research maps into and works with the tools that we're building. We'll be running visiting fellowships and hack weeks to start training out the community, so we as a community can learn how we do Rubin science at scale. And these workshops, incubator projects, visiting fellowships and hack weeks, we have funding to support these things. So our goal is to build an inclusive community So it's not just that the largest institutions have access to the ability to do science, so that we can maximize the type of science that comes out, and can we maximize the discoveries that will be made with Rubin. Okay, it's a 5-year project. We're initially in the first 2 years of it. We're actually about 3 weeks from our first hire, since our first hire. And so we're in the stage now where we're in the design workshops to understand what are the needs from the community. The first couple of years, which will correspond to the time when Rubin is completing its construction and then moving through commissioning. For us, that will be the commissioning and the development and the commissioning of these science applications, running them on precursor data sets. And so that when Rubin starts its 10-year survey, that we're in a place to start developing or applying these algorithms to the Rubin data themselves. You will hear many times over the course of the next couple of days that we really want to focus on the first 1 to 2 years of Rubin and the science that we can achieve with that, because we'll learn so much in the first 2 years that the science that we end up doing at the end of year 2 may look very different from what the ideas we had going into the project. And so we will have time in the 3rd year and onwards to start reflecting back on how the tools work and what the next level of development that we actually want. So with that, I am going to turn it over to Rachel, and we're going to talk about some of the goals for this specific workshop.
Thanks, Andy. Okay, hi, everyone. I'm Rachel Mandelbaum. I'm very excited to be here. Like Andy, I haven't been at a workshop in person for more than 2 years. So if it looks like I've forgotten how to be a person at an in-person workshop, that's because I may actually have forgotten, but I'm very happy to be here and looking forward to relearning. So as Andy said, I'm going to kind of talk through the goals of what we're hoping to accomplish together for the next couple of days. Okay, so there are kind of 2 top-level goals of this workshop. One of them is to enable the interactive development of exciting scientific use cases for early LSST data and identifying common computational or technical challenges associated with them and the technologies that will enable people to carry them out. The second goal is to promote the development of a broad and inclusive community of researchers engaged with linked frameworks. So the overall schedule of this workshop and the design of the plenary talks and the communication channels, which we've made fairly open to anybody who's interested, were all developed with both of these goals in mind. Okay, so how are we going to do this? How are we going to all kind of interact here? So the plenary content is going to set the stage, and you'll see that there are talks associated with the science, the LSST science, with the technology, with the software, and with inclusive collaboration. And then we'll have breakout sessions. So there are 2 breakout sessions that are organized by scientific areas, focused on developing science use cases, following a template that will prompt us to, think them through in a sort of common way, thinking through challenges and so on. Then there will be one session organized by cross-cutting technical challenges. Those will be gleaned from the science breakouts. So as we're reporting back on our science use case breakouts, everybody will be encouraged to think about what are some of the common challenges across these, so that we can then talk those through, the technical challenges through in the technical breakouts. And there will be one session on inclusive collaboration focused on how do we build an inclusive community. So the first 2 of these will have a plenary report out session, and all of them will have a written record that everybody who's interested in the workshop can see, so that participants can all learn from each other on these topics. Okay, so just as a starting point, I wanted to remind you a little bit of some of the homework we had sent in preparation for the meeting. It's not too late for some of it, so if any of this looks unfamiliar, I want to encourage you to take a look. So the first thing was to provide a single introductory slide about yourself. Those are to be presented during the breakout session so that the people involved in the breakouts can get to know each other. And so those start Monday afternoon. So this afternoon, sorry. Um, the second was to provide an example of a high priority and high urgency LSST science use case. So those are things that we're going to be fleshing out in detail during the breakout sessions that start this afternoon and then continue tomorrow. But of course, it's great to have a starting point. So even rough initial drafts are great, and I saw that many of you have provided initial drafts with at least some of the content. So that's great. And the last thing was to read some material on inclusive collaboration, for which there's a plenary talk in this session, but then the breakout discussion is on Wednesday morning. And so if you didn't have the opportunity to read that yet, I do encourage you to do so before Wednesday. We hope that this material has gotten you thinking and sort of prepared to work together towards the goals of this meeting. Okay, so what are we trying to get out of this? So as scientists, we all get the opportunity to think about our high priority and high urgency LSST science cases, the technical challenges and enabling technology. And one of the key things that I hope we'll get out of this, and that may be new for some of us, is the opportunity to make connections with and learn from others who are working in different scientific areas. I can say, as somebody who's invested a lot of time and energy into one of the LSST science collaborations, it's been a great opportunity for me to work in depth with people in my scientific area. But I've had less opportunity to work with people who are interested in other LSST science. And that's something that I'm really looking forward to at this workshop. And I hope that you all are as well. Like me, you probably looked at the list of participants and said, here are some of the usual suspects that I know. And then there are many people who I don't know who work in other science. So this is kind of a chance for us to work together in a way that we might not have before. So there are also many people here from Rubin Observatory, NOIR Lab, and teams are developing independent data access centers, IDACs. So individuals from those groups are going to benefit from hearing in detail about the intended community software and data usage patterns once LSST survey operations start. And members of the LINC team, as Andy described, will identify opportunities to develop cross-cutting technology that broadly enables the LSST science community. So we hope that there's something in here, or multiple somethings in here, for everyone. And as part of that, we were thinking, how can we make sure this workshop has an outcome that supports those goals? And so besides just having the experience of working together and maybe finding potential new collaborators, our plan is to use the workshop material, the science use cases and the technical use cases and the discussion of inclusive collaboration to develop a white paper that will be open to the entire LSST science community. So, we'll work openly on, LSST community and Slack and so on to make this really open and include the following content: the science cases drawn from the LSST science community, the common computational challenges and enabling technology, and inclusive collaboration strategies associated with software development and scientific collaborations. So of course, lots of people have thought about these topics before. There are science roadmaps associated with LSST science collaborations and other documents. But we're hoping that the cross-cutting content, scientifically and technologically cross-cutting content in this white paper will make it sort of complementary to that previous work, and it should serve as the basis for future collaborative efforts across the community. So that's it for the intro to the workshop, but I wanted to close by thanking the organizers, and there are a lot of them, because there have been people thinking about scientific organization. There have been people thinking about the inclusive collaboration aspects of this workshop. And of course, there are administrative staff here at the CCA who have been working tirelessly on the logistics as well. And so here's, all the pictures of people on these various groupings. And I particularly wanted to flag Fatima and Kristen, who are here in person, and have been key local administrative staff and organizers for this workshop. And besides this group, we've also gotten a lot of input on this workshop from others, like input like from the chairs of the LSST science collaborations and many other members of the community, who who sort of gave input on how we could make this impactful for everyone. So I want to thank this group and everyone else who provided input to this workshop. And with there, I will close, and we're happy to take questions.
Could you use your seat mic, please?
So do you have a sense of if the participants actually represent the broad science coming from LSST? And if we don't, are we going to try to fill those holes, or do we just want exemplar use cases to flesh out? We don't need to cover the entire breadth of science.
Yeah, so that's a great question. So when we had the initial call for expressions of interest to attend, we asked people to identify affiliation with groups like Rubin Observatory or LSST science collaborations, and also to put like an example of some of the science they wanted to do. So from that, I would say we definitely have broad representation. For example, there are people who are members and who are active in all of the LSST science collaborations and in Rubin Observatory and NORLab. But the fact is LSST science is really vast. So, I'm sure that there might be specific use cases where we don't have someone who's necessarily going to think about that. So we should think of this as a group that can broadly represent the science, but of course it is examples.
Maybe just to add on to what Rachel was saying, you shouldn't feel constrained, though, to just talk about your own science. If you have been involved in, for instance, the Galaxies Working Group, and you've been involved in discussions about the kind of the great science that people want to do with that, and you want to present that as a potential idea that then we can work through as a group in terms of the use case, you should feel free to do that. It doesn't have to be just your own science that you're particularly going to work on. We want to try and capture as much as possible. So don't feel constrained in terms of what you want to discuss.
The fact is, since we're working in the open, for example, if somebody here were to bring up an example of, oh, I think this is really interesting, I'm maybe not the best person to figure out the details, they could bring it up, and then, we could try to draw someone else in to comment on the details.
So I get the overall idea about Link, about developing science frameworks and collaboration, because we might not all have the software skills and whatever. Is the idea behind Link is also that it will be providing hardware to be running that sort of stuff on into LSST, so we don't need to worry about trying to find that to do the types of science analysis we're interested in as groups?
So it's a bit of a mix. So we do actually have resources as part of Link. We have a collaboration with the Pittsburgh Supercomputing Center, who are providing, I believe it's 5 million CPU hours over the first 2 years on Bridges, which is I guess is a machine learning platform as well as a kind of a traditional HPC system. We have resources to do development for cloud computing. We're talking to a number of the cloud providers to see if we can enhance those resources to make it something that we can work at scale. I think the way that we've been thinking about it is to try and provide sufficient resources for us to be able to demonstrate that these projects work, to validate them, to do some of the science. But it is likely that if you're doing a large scale, it takes 100 million CPU hours to do your science case, which may be true for some examples. I mean, for example, some of the cosmology work that may happen. Then we would actually go back to either through supercomputing center grants or through cloud computing resources that are available through NSF and DOE and use those resources. So I'd say we have enough resources to get going, to do science, do example science, to work with precursor data, and we're happy to, and we'll make those resources available to the community so we can actually build out some of these cases.
Thanks.
Could you use your seat mic, please?
Can you hear me? Amazing. Do you have plans to publish data on the, I know you did a lot of work on curating this group, the diversity of this group. Are you publishing those statistics or that data on where people come from and their career stages? Or would it be possible to have access to that?
I think we're not planning to publish detailed information, but we can definitely provide the broad breakdown of the group of participants across career stages. It's, I mean, I can say now it's approximately, if we consider the in-person and full, like people participating fully in the workshop remotely, it's approximately a third graduate students, a third postdoc, and a third either faculty or permanent staff.
And the permanent staff includes Nora Lab, Rubin. Okay.
Yeah, or national labs.
What about nationalities? I was just curious because I've met some people here from Mexico already, and that was exciting.
Yeah, I don't want to try to say off the cuff because I'll say something wrong.
Okay.
Could you use your seat mic for the people on Zoom, please?
Here we go. Ah, I got it. Okay. I thought you had to hold it down. Sorry. Just to add to Andy's answer on the hardware resources, so the independent data access centers, which Rachel mentioned, right, do have a lot of CPU and storage that they'll be contributing as in-kind contributions to Rubin, and figuring out the pairing between problems and what's available in terms of resources is something we are going to be discussing later this year in a workshop that we're organizing, and so we're very interested in that problem. So that's there'll be a large number of resources available. How to get the problems to them is the thing that we need to work out.
I'm still having difficulty in placing how exactly the link frameworks falls in place with, say, the project and the science collaborations. Do the software engineers and research scientists in the link, do they work within science collaborations, or are they independent of science collaborations? And who are the consumers of the outputs that they produce? Is it available to anybody with data access, or again, just to science collaborations?
Maybe I could start this one and then Andy might want to follow up. So there were a few parts to that. So to start with, I'll say the plan is to provide open source software. So it would be available to anybody, regardless of whether they, are a member of a particular group like an LSST science collaboration. So our hope is to collaborate and coordinate our work with the science collaborations and with Rubin Observatory and Nora Lab, as appropriate for the problem. So in some cases, excuse me, in some cases, if, for example, some science collaboration has already produced a software tool that is, key to some science case, we might say, oh, maybe we'd like to collaborate on that tool. In other cases, there might be less software in place, and we might try to produce something that multiple science collaborations would adopt. So it depends a little bit on the scientific area and the technology and the current state of work in that field. But we hope to coordinate effectively with all of these groups and find the right way to collaborate depending on the area. Andy, do you want to add anything to that, or?
I just say that I think we all recognize that there's limited resources, both within Link and across the collaboration, the science collaborations as a whole. And so we're not looking to reinvent anything. We're looking to collaborate to try and find where the holes are and see if we can actually fill those holes.
Thank you. Yes. So my name is Federica Bianco. I'm at the University of Delaware. I wear a lot of hats, both at the University of Delaware, at the Department of Physics and Astronomy, and at the Biden School of Public Policy and Administration and Data Science Institute. And within Rubin, where I've been the chair of the Transient and Variable Star Science Collaboration for, I can take off my mask, right? I'm far away. I've been the chair of the Transient and Variable Star Science Collaboration for longer than I care to remember, and the Science Collaborations Coordinator for over 5 years. And this will be my last talk, I think, as Science Collaborations Coordinator, and my first talk as Deputy Project Scientist. So I was very nervous because I better not mess up the exit or the entry in either roles. And messing up the exit will be really, really hard because I'm just going to talk about all the amazing science that can be done with Rubin. And I have a lot of material that has been prepared for many, many years by all of the amazing people that work in the science collaboration. So all that I'm going to talk about and I'm going to present, all the graphics are primarily done by the science collaboration members. So of course, we're talking about Rubin LSST, and you may have heard that Rubin LSST has 4 science pillars around which the telescope and the system altogether was designed. And something that was not clear to me for a long time is that these are not really the science areas necessarily in which Rubin wants to focus. Certainly, they're not the exclusive science areas in which Rubin will focus and on which Rubin will be transformational. But there are 4 areas that were chosen to design the system around, such that a system that can be transformational at the same time in all these 4 very different, as you will see in a second, science areas, it really will be transformational and have amazing potential of discovery in astrophysics across as many domains as you can think of. And so the 4 science pillars are the dark sector, dark energy, and dark matter, which will be probed by Rubin through exquisite measurements of strong and weak lensing, large-scale structure, clusters of galaxies, and supernovae. Mapping the Milky Way and the local volume with a resolved stellar population of 17 billion stars that will be characterized in shape, color, with many filters and their variability. It will build an unprecedentedly large inventory of the solar system, including collecting orbits for over 6 million objects, and this goes from the very near Earth orbit objects that are potentially even hazardous for our own life, all the way to the Oort clouds, and then more recently, a lot of focus on interstellar objects. And finally, the one that is dearest to my heart is the exploration of the transient and variable universe. And I think it's also interesting how these 4 topics were put together, how you're probing dark energy and dark matter versus cataloging the solar system versus exploring the transient and variable universe, which I think is a reflection of kind of like the state of the field in these areas. We really are in a phase where we are exploring the transient and variable universe. There are many phenomena that we don't know yet. There are many phenomena that we haven't even predicted yet, like true anomalies that we are not even thinking of. And Rubin has an enormous discovery potential in exploring these unexplored areas of the parameter space and therefore discovering brand new things both morphologically and in time domain. So these 4 science areas constitute the pillars around which the survey is designed. But this is not to say that all other areas that you don't see here. So for example, a very glaring area that you might not see here is if you're a person that studies galaxies. This is not because Rubin will not do galaxy morphology to a revolutionary degree. It's simply not one of the goals around which the project was designed. but the characteristic that makes it awesome in these 4 areas will enable incredible studies of many other things. So I mentioned the science collaborations, and probably everybody here knows what the science collaborations are. They are 8 groups that are self-managed and self-organized. They're not formally part of Rubin Observatory, although we are now federated and recognized by Rubin Observatory as of about a year ago. That are organized around science themes, so around the expertise and interest, scientific expertise and interest of their members. And that work, however, as sort of graphically demonstrated by the network on your right. The work as a network is a very interconnected network of scientists that studies astrophysical phenomena across these themes. And those are the AGN, dark energy, galaxies, informatics and statistics, solar systems, stars, Milky Way, local volume, strong lensing, and transient and variable star science collaborations. And they range in size from a few tens to a few hundreds. I have to confess that this graphic is a little bit out of date. So I believe that all of the science collaborations are a bit larger now. And I've recently done a census of the members to enable the election of the next science collaborations coordinator, and we are exceeding 2,000. All right. So I think you can sort of split in your head, perhaps, the science that Rubin will do into 2 broad categories: time domain astronomy, so time domain science, and then static science on the other side. However, this is kind of a trick because a lot of the science will live at the interface of these 2 domains. And so some examples of that that I think are particularly obvious in terms of still referring perhaps from now on to broad areas of research by lieu of their science collaborations, strong lensing and AGN. Both of them rely very heavily on both the static science, the catalogs, and the morphological, the resolution and accuracy property of the images of Rubin that enable morphological studies, as well as on the time domain enabled by Rubin. And so, for example, the AGN science will benefit tremendously from an enormous increase in the number of objects that will be known. Rubin will discover about 50 million. It's expected AGN down to redshifts which that are not accessible right now, redshift of 7.5, but will also benefit from the study of variability, microlensing, etc., blazars and other phenomenology related to AGN in the time domain. And strong lensing as well can grow in cosmography from lens time delays. And this is an area that the strong lensing science collaboration works together with the strong lensing group within the desk, as well as studying the resolve properties of galaxies at high redshift that were inaccessible to us until now, and calibration of cluster mass functions of which will come from the joint analysis of strong and weak lensing, getting us much closer to probing dark matter. Sort of similarly, you can think of science that can be done on the alert system of Rubin, science that can be done on the catalogs, and science that can be done directly on the images, and particularly perhaps on the deep image stacks. But this is also a trick because in reality, a lot of the science will be done on all of these things at once. And I'll go into some very, very brief overview of what the data products are. I think most of this audience should be familiar with it, but I'll have a couple of slides in a second to clarify what I mean by alerts-based and catalog-based, etc. Just very broadly, one of the things that will make that will enable science that has not been done before, the way I kind of like to think about it, is that because of the image property of the high resolution and exquisite image quality of the Rubin LSST images, but also of the large area of sky over which these images are accessible, I kind of think about it as having maybe something that is close to an HSD image for every area in the sky, which in the southern hemisphere sky, which if you think about it is kind of insane. And these cover really truly all of the southern hemisphere sky, which will be covered with tens, in fact, hundreds to thousands of visits. This, which I'm showing here, is just one of the potential and perhaps even a fairly outdated one footprints that Rubin will collect. The exact details of the footprint, as well as the exact details of the strategy with which the footprint will be observed, are still to be determined. But you also see a lot of symbols on this particular map that refer to different kinds of strategies that will be implemented in different areas of the sky. So the majority of the sky that you see here with a green color that sums up to about 800 or so visits, that's the wide fast deep, which is the main Rubin survey. And so the wide fast deep will cover homogeneously 18,000 or more square degrees of skies. But there will be a lot of surveys that accompanies the wide fast deep that will take advantage of the extra time in the tenure of the Rubin's operation. And this includes, in this particular image, you see a galactic plane GP, so a survey that would cover the galactic plane footprint with a strategy that is different than the one that is constrained by the four science pillar that I mentioned earlier, which will be implemented on the wide fast deep, a strategy that might be tuned to really enhance galactic science, whether that means variable or through stellar results, stellar population. Similarly, the north ecliptic spur, the south celestial pole, and then you see the four deep drilling fields. Four deep drilling fields that have been selected because they are legacy fields like the Chandra Deep Field South, etc. Legacy fields that have a wealth of observations in multiple wavelengths that will enable multi-wavelength studies of anything. They're extragalactic fields, so of anything primarily extragalactic that will go down to a deeper and denser, deeper image stack and denser cadence. And we just announced the Rubin Survey Cadence Optimization Committee, which I now chair as part of my responsibilities as Rubin Science Deputy Project Scientist, has just announced an endorsement of the Euclid field south as the selection for the fifth deep drilling field. Again, thinking about the science that is enabled by joint observations and joint data products, thinking about specifically the joint data product work that is being done on Euclid and Rubin. Let me give you some maps that really make the case for how transformational Rubin can be and can give us an in into understanding what science can be transformed. So these are 5 sigma depth maps. So this is the depth at which a single image, the median image on the left, there are median images, right? On the median image for the full 10-year survey will be collected in the G band. I have the G band twice. I wanted to put the R band there, but it's not very different. And on the right side is the co-added depth. So these are co-added depths that go as high as magnitude 28. This is going to enable, very trivially, just because of its depth, is going to enable studies into a very much further universe at scale. Another really critical parameter is a median intra-night gap. So if you think about this, you can, especially for the co-added stack, you're thinking perhaps of the static science that Rubin will enable. But for the time domain science, the intra-night gap is really critical, and the inter-night gap, so the gap between observations within the same night and between 2 nights. So the intra-night gap is Rubin. The long story short here is that Rubin will collect more than 1 images per night. So phenomena in the time domain that vary on time scales of hours will be accessible, even though hours is a particularly tricky time scale, because as you see, the intra-night gap is actually shorter than an hour here. But there are potential surveys that would collect 3 images, for example, for every field in the night, so enabling our timescale observations. And the internight gap is between 3 and 15 days, so few days repeat for the same field and multiple images of the same field every night. Another really important characteristic of Rubin is its astrometric precision, which will enable a variety of studies. Here I'm showing parallax errors, so to enable studies of the galaxy, but also distinguishing, for example, between extragalactic objects and galactic objects for the selection of quasars out of stars that just by color would be very difficult, that can, however, be enabled both through variability and through exquisite parallax measurements. And not only this, but there is a healthy community that studies astrometry with LSST. And this kind of precision enables, I think I'll have a slide on this later, even very exotic types of analysis, perhaps, that relies on differential chromatic refraction, where you leverage the atmosphere, which Rubin can observe at different air masses, and the apparent motion that that causes for the objects, which if you have this kind of parallax, tiny parallax error, this kind of astrometric precision, you actually can measure, and that can tell you about the color of something, even in a single image, just because of its position. All right. So in the time domain, let me go over briefly what I think is mostly revolutionary. This perhaps is going to be a slightly biased time domain talk. I am, after all, a time domain scientist and the chair of the Transient and Variable Star Science Collaboration. I'm trying to rebalance, but bear with me. So the characteristic time scales, this is kind of like the way in which transient astronomers like to think about the universe, right? So you have characteristic time scales on the x-axis and brightness change, relevant brightness changes on the y-axis. This is in peak magnitude, in absolute magnitude, but this displays things that are broadly accessible to Rubin because of its sensitivity. And so the time scales here go between seconds and decades. And the length of the survey for Rubin is 10 years. So that enables secular studies of time scales that vary over years. And it is particularly interesting for phenomena such as great eruptions, like the Eta Carinae great eruption, of which we have exactly one example, which lasted a decade, as well as extragalactic studies of variability, such as, for example, those relating to AGN. But also, like I said, it will enable intra-night observation. So it really does cover wealth of the x-axis range of this plot. And you may notice that here I put a lot of labels for all the other things that are in this plot, which is very convenient. There is a big gap into what we have observed in that area, so I can put the label there. But this is a very interesting and intriguing thing, because it is possible that nature just decided not to put anything interesting sub our timescales. It's also very true, though, that we do have an observational bias. Now, Rubin doesn't directly address that observational bias. It's not really designed to do intra-night high cadence observations, but some of the surveys that I mentioned that will accompany the Y-FAST-D may access those timescales very critically. And this is from Marshall et al. 2017. This is a white paper that was written by members of the science collaborations. And again, this emphasizes that we're interested in timescales that go between minutes and years and decades. And we have scope science that it will benefit from all these timescales. How am I doing with time? I don't see I see the clock there. Okay. So I put together these slides. I was trying to put together a bunch of photos, but they got super overwhelming. So I removed all the photo and I put words here. So at the top, you see, and I will go also science collaborations by science collaboration over each one of them with some critical science deliverables. But so what you see at the top is the science collaborations by their logo and symbol. And below are some of the things that they can do. For example, like I already mentioned, AGN, in time domain astronomy. So AGN selection and variability studies or studies of blazars will be broadly advanced by Rubin. The Stars and Milky Way local volume, for example, has a wealth of science that comes from studying how the stars vary. That include just the study of variable stars and the nature of their variability to near field cosmology, and using variable stars as distance ladder to link with extragalactic standard candles and accretion flow indicators and progenitors of explosions, as well as many other areas of study. And of course, the desk I want to mention that a lot of the cosmological probes are related to time domain astronomy, including, of course, the Nobel Prize winning supernova type 1a cosmology. But now we're entering a really exciting area for both the desk and TVS that are and the strong lens and science collaboration that are extremely interested in the multi-messenger astronomy and understanding the nature of multi-messenger phenomena, whether they are neutrino emitting or gravitational wave emitting, as well as their potential applicability as new cosmological scales. Let me skip over this. I think I made this point before. The survey strategy is still to be defined, and it may vary quite a bit, both in the footprint and in the time gap distribution. But let me say that not for long, because we are nearing the end of the process of creating a recommendation for the director for the final survey strategy, which should be, in fact, completed by the end of this year. So let me focus for a second on static science. And the way I like to start thinking about it is by starting with this SDSS image morphing into the LSST, simulated LSST corresponding image. And in fact, I like it so much that I'm going to go back and do it again. Oh, no, it won't do it again. Ah, that's so sad. Okay, here goes. So clearly, all of the static science, all of the science that relies on catalogs is going to be tremendously enhanced just by the sheer number of things that we see that we couldn't see before. Of course, that comes not with many complications, comes with many complications. Yes, that's what I wanted to say. And having software engineering plans for this is really, really critical, because at this level, at this depth, and at this resolution, everything is blended and everything is variable. So doing static science requires an enormous amount of development in terms of the algorithms that we use just to extract the catalog properties of these objects and combine. There's a whole long story about catalog matching at this depth and resolution with these number of objects. So really critical work to be done there. There is already, of course, being done by the science collaborations, by a member of Rubin, et cetera. And then one thing that certainly is worth mentioning is that the Rubin photometric system was built really thinking about deriving exquisite Rubin photometric redshifts, and was designed for photometric redshifts with random errors that are smaller than 0.02 and bias that is below 0.03, and with few outliers. And there's a lot of work done on this by the Rubin team, particularly by Melissa Graham, but also by members of the community. I'm thinking Amanda Banniger and Alex Mize. And this will be a pillar for all of the extragalactic science that Rubin will do. And so similar slide to before, all the science collaborations and all of the amazing science that will do and how it will be advanced in the static science domain specifically. Let me mention morphology that will be extremely relevant for really all the science the extragalactic science collaboration. So AGN studies will be advanced tremendously by morphological studies, as well as strong lensing, as well as galaxy science. There will be access to low surface brightness regime that was inaccessible before. And of course, cosmological studies that go through sheer and really accurate measurements of the image that galaxies have as deformed by gravity, as well as the power to resolve star, which will greatly enhance stars making local volume science and transient variable star science. The TVS thinks a lot about how the catalogs will enhance time domain science by giving us access to progenitors, directly observed progenitors of transients that we didn't have access before. And I'm neglecting the solar system, and that's terrible, and I don't mean to do that, which will obviously advance by both time domain science and studying the variability of objects, and by studying the colors and shapes of solar system objects. Like I said, I have a very quick slide on what are the data products. Rubin will deliver 10 million. I'm going to say it again. Rubin will deliver 10 million alerts every night. That means 10 million things that changed in the night sky compared to our template vision of that patch of the night sky, which will be delivered to the community through softwares called brokers. And I'm sure we'll talk about brokers here, and I know that there are many members of the brokers team in the audience, to the entire world. This is a data product that is worldwide accessible without requirement for data rights. It will also deliver prompt data products, so essentially reprocess and enhance alert 24 hours after the delivery of the alert. Oh, and I forgot to say the best part, that the alerts are delivered within 60 seconds of shutter close. So that doesn't mean that the transients are 60-second old, of course, because really they're as old as they are from the time that you were looking at that sky before. But if you might be so lucky that they might really be second old phenomena. And it will release a catalog, annual catalogs every year that will collect both the history of the transients detection, as well as the catalogs derived from the co-added stacks, so the co-added images that will grow with the data collection every year. The last two data products are proprietary products, so only members of the data data rights community, which, however, means the entire US and the entire Chilean community, as well as many other international communities that are joining through the delivery of in-kind, the exchange with in-kind contributions. Okay. I think a change of perspective is required, though, to do science with Rubin. And what I mean by that is that the way, and I think this was mentioned earlier, right? So the way in which we used to do science by downloading fixed files, as Julie mentioned, or by directly accessing images, or even by let's just say by directly accessing images, I'm going to go into a little bit more depth in a second, has to change. So there's an enormous amount of potential in just the sheer discovery of things, and these are fairly old thoughts by Stephen Ridgway from a paper called "The Variable Sky of Deep Synoptic Surveys." But I remember that he used to give talks about this, and the talk's title was something like "Why I Learned to Love and Stop Being Afraid of the Number of Alerts that LSST Will Deliver." Because at the beginning, it's going to be extremely overwhelming how many things Rubin will discover that are entirely new. This rate of discovery will go down for things that repeat. It will go down for solar system objects. In the last 2 seconds, I was trying to pull out a slide that shows the discovery of new solar system objects and how strongly peaked it is at the first year of the survey. And so what will continue to be discovered at the same rate are stochastic events, such as supernovae and proper transients that are not repeated and are not and are really truly stochastic. So all of these things will happen at their own rate, though. So I think a lot of the science deliverables will suffer a significant amount of confusion early on that will then be mitigated over time. But this is definitely something that we need to think critically about, and we are thinking critically about. I'm thinking, for example, of the great advancing in photometric classification for transients brought on by the desk and TVS-led photometric challenge, the plastic challenge. And examples of things that will enter statistical regimes where before they were a single, I've seen this once and it was so interesting, and I'm trying to get everything out of this particular phenomenon, like just I already mentioned, like Eta Carinae, of which we have exactly one example. And those things have the potential to enter the era of statistical studies. Those, as well as strong lensing, of which there are a few hundreds of examples now, but are expected to be of the order of 10 to the 5. Something like the Great Eruption, which we have seen from Eta Carinae. Eta Carinae is a star that is like really next door, and that's the reason why we've seen this eruption. It's not an explosive event, so it wasn't bright enough for us to see it in other galaxies, really, but it will be bright enough for us to see it all the way to Andromeda with LSST. Okay, I'm going to go think I have enough time. I'm going to go through very quickly through each science collaboration, each science case, starting with the desk. The desk has a very clear and well-defined science case of studying the dark sector. So that means cosmological constraint that will come from both time domain and static sky. And the system is really designed with this in mind, because the requirements that these kind of science, such as the astrometric precision and the image quality that is needed for doing weak lensing at this scale, are really constraining. And so this is a large, put a large strain on the system design from the very beginning. Strong lensing, like I mentioned, will increase, the sample size will increase by a few hundred to 10 to the 5 lensing, with a lot of potential for studies that have barely begun now. Time delay cosmography, galaxy cluster mass structure, which will put together strong lensing and weak lensing, and can be an extremely promising probe for dark matter, but also quasar microlensing, and just generally morphology of these things, of which we've seen just a few examples, but the morphological parameter space is enormous. Similarly, galaxy will benefit tremendously from both the depth of Rubin and the image quality. This is an image from the majority of the plots where I don't put the name. Oh, I did put it there. Where I don't put where they're from. They're from USH 2019, which I'm sure many of you were probably co-author of as well. And this is an image of a galaxy at the top as it was seen by SDSS. And at the bottom, as it was seen by the music survey. And this is a little bit fainter and a little bit less, less accurate image, as less excellent image properties than Rubin will have. So about 1 magnitude fainter than Rubin will see. So I think this makes the case for itself about how any study that rely on morphology will be just enhanced enormously by Rubin. And that enables studying of galaxy evolution across redshifts, because it will go down to extremely large redshift, as well as things like the rarest and most exotic, discovery of the rarest and most exotic forms of galaxy mergers and galaxy shapes. So AGN's I want to give a shout out to the AGN Science Collaboration for working very hard over many years to collect multi-wavelength observations of fields of interest, particularly the deep drilling fields. And we now have this legacy of multi-wavelength observations over patches of the sky that will be of incredible usefulness for AGN studies that are really multi-wavelength in nature. But I have this slide here. The slide itself is from Dickinson 2014, but I heard this point being made by Amanda Manager, who's the co-chair of the Galaxy Science Collaboration, in an AGN talk about how really this very quick parameter space of redshift, and this ends at redshift 6, it's expected that Rubin would detect a higher redshift, where we have, it doesn't really matter what it is. It's star formation history and black hole accretion history and how they're comparable. But the point is that different regimes in this plot will be accessible through Rubin by different probes, by low surface brightness sensitivity, as well as time domain. Another interesting thing that I said I was going to mention again is DCR. So the AGN science community, but also this is now happening in the Stars and Milky Way local volume science collaboration, is trying to extract color information beyond the filters, the simple collection of colors by the different filters, by images in different filters of Rubin, to get intra-filter information, but also to get information on very elusive time domain phenomena that are observed in a single filter through differential chromatic diffraction. And this can really enhance our understanding of the spectral energy distribution of quasars, but I'm going to argue also of variable stars and flares. Stars Milky Way local volume. The slide on the left just shows the access space that Rubin will enable, which has been completely inaccessible right now. So you see the Gaia access space in a color diagram. With the rainbow chart, you see the area that Gaia has covered. At the top, you have the SDSS limit, and above that is Rubin. So this will be populated. And the Milky Way structure will benefit from 20 billion or maybe 17 billion resolved stars, plus their information in time domain. And this will really greatly enhance local volume and solar neighborhood, I meant in this case, solar neighborhood studies. TVS works on transients all sorts and variables all sorts. So we're interested in extragalactic transients, including fast transients, supernova, tangential disruption events, as distance scales, but also as because we are interested in studying their natures, and as well as galaxy variability. So binaries, magnetically active star, microlensing, non-degenerative variable, transiting planet, pulsating variables, all of this, the majority of this field will enter for the first time, really statistical samples, thanks to Rubin. And all the rest will be greatly enhanced by the growth of the samples and the growth of the accuracy of the measurements. And also we think a lot about anomaly detection and true novelties, like I mentioned earlier. And last but certainly not least, the solar system will be enhanced by the characterization of the orbit for many more objects for which we don't have the orbit characterization now. And this is the standard plot from UVSH 2019 that shows how we can differentiate different families of objects in the solar system down to distances that were previously, of course, inaccessible at scale. And what that will do from a scientific point of view, it can help us reconstruct a kinematic history and so an evolution history of the solar system, and also put our solar system in context of planetary systems in general. There's a potential to study mass loss in asteroids and comets. A lot of comets will actually be resolved morphologically. We can access the Oort cloud, which, like I said, has been barely accessible to surveys until now. And of very much recent interest after the discovery of Kamehameha is to catalog how many interstellar objects might actually transit by us. And there's the perspective that, with very large uncertainties on the numbers, but the perspective is that tens of these objects will be discovered by Rubin. Finally, I want to mention that there is a lot of science being done by the informatic and statistics science collaborations that works with all the other science collaborations to help develop methodological advances. So you can think about it as a data science collaborations. And while I thought that it was appropriate in this talk to focus on astrophysical science in terms of what astrophysics is going to be enabled, Rubin does enable advances in data science with the enormous and extremely complex data set that it offers. And that work is done primarily inside of the informatics and statistics science collaboration, but in all of the other science collaborations collaboratively as well. I think maybe I can just stop here. I have more slides, but I think I said all that really needed to be said. And I'd rather leave some time for questions.
Okay, I think it's on. Thank you so much, Fed, for this really wonderful overview talk. It was great, and I'm very excited for LSD. I don't know if this is the right place to ask this question, but I'm curious if you, and this is just coming from a very naive place, can you tell us about what's the status of PhotoZ estimates that will come from LSST? I know there is a very impressive. Okay.
There are so many people that are experts.
Oh,
in
no.
This room.
Oh, great. Yeah.
I really think that I'm not the best person to answer this question. There's a lot of development. Andy, Alex would have such great answers that I really appreciate the question. And it's really pivotal to a lot of the science that I described. Let me just punt on the answers so that an actual expert can answer.
Thank you so much. At the coffee break, I would love for someone to tell me.
We probably have 30 seconds if there's an expert in the room who would like to answer it.
Hi, Will. Could you use your seat mic for people
Hi,
on
Lisa.
Zoom, please?
Okay, so so the data management group is doing some work on, is working very closely with the community to determine what is the best algorithm to run to compute photometric redshifts as part of the science pipelines. There are many different algorithms and ways that you can do this. We don't expect that LSST, the project, will run all of them, but we do want to choose a photometric redshift estimator that will satisfy the vast majority of science cases. And it would then be left as a user-generated activity and exercise for experts who are investigating new and novel ways of computing photometric redshifts to run that, possibly in the LINK framework. The project will provide an estimate of photometric redshifts for all objects. Which estimator we will use is currently not determined. We're working with the community, and we will trial different algorithms through the commissioning period and work with the community to understand what gives the best results for the vast majority of science cases. The tech note is, I can write it up or give it to you later, but it's DMTN 049. We've already held one, what we call session with the community. We've put out a request for letters of expressions of interest for photometric redshift estimators to run. We got a large number of them, and we're going to move forwards trialing them during commissioning.
Thank you.
Okay, this is a question from Zoom. How does a person go about joining a science collaboration?
Oh, I love that question, and I love that. It's probably the last time I answer. It will be the business of the next science collaboration coordinator. So all of the science collaborations are extremely accessible. They're really designed to be a supportive, inclusive environment where you can grow your science skills in a particular area, learn about the potential of Rubin, and contribute to preparedness and discovery with Rubin now that we are entering the discovery phase. But they're all extremely accessible. All of them have an access to, at least as one of the tier membership, just joining the science collaboration and being in the loop and being connected to communication channels such as the Rubin Slack that allows you to know what's going on. And many of them have a multi-tier membership where if you are interested in contributing more seriously and committing some of your time to those to work for the science collaboration, whether that's service or science development, or probably both, then there's higher tier membership that come with rights to, for example, publication, being part of the publications that do come out of these science collaborations. Each one has its own specific rules. They're all open to all data right holders, and many of them have ways to join, at least provisionally, especially if you are in a community that is trying to acquire data rights. And I do encourage everybody to join the science collaborations. And the easiest way to find out how is to Google Rubin LSST Science Collaboration. That will take you to the site of the LSST Corporation, which hosts a link to each one of the science collaborations websites.
Second Zoom question. What kind of deblending will be carried out in order to produce the individual measurements of each source in the catalog? How will the fluxes be estimated in this case? And is this already implemented?
So that's not an answer that I can give in a few minutes. And this is also an answer that the many experts in the room should answer on my behalf. But what I want to say is that there is a lot of work going on deblending that leverages everything from traditional methods to heavy artificially intelligence-based methods that goes on both in Rubin data management as well as within the science collaborations, and a lot of it goes on together between the two groups. And many algorithms are being explored and applied. And also that is true for crowded field photometry as well, which is a related topic.
The slides at the beginning were really helpful in terms of the depth as a function of position on the sky, and I can imagine those being really useful in some of the discussions that we have over the next couple of days. These are available online, is that?
Yeah, because I run it through a web browser. It's accessible directly as a link, but also I downloaded them on the Dropbox. Now, I might have made some changes. I'll download another copy.
Okay, thank you.
About those slides, I had a me question, and that was what is 5 sigma depth What's
Yeah.
internight gap and what's heel pix slicer?
Okay, so sorry, the first one was 5 sigma depth.
5 sigma
That
depth.
is how faint something can be when to be detected with an uncertainty of 5 sigma, which means with like very, very small uncertainty, 0.00, what is it? 0.00003% uncertainty, so something very, very small. What was the internight gap? So that's the time that passes between two observations, and there's two critical metrics that I plotted: the distribution of how much time passes between two observations within one night, because there's always two observations in one night, because that's necessary for solar system. It really facilitates solar system studies. And then what is the revisit time of that field in a following night? So how many days between observations and how many observations in a night in which you observe the field?
And that's all part of
Yeah.
strategy.
Yeah, so a lot of that is trained already by making sure that you get to the 4 science pillars. So we know, for example, that we need to take 2 images within one night to a distance of like no more than a couple of hours, right? So that will enable the solar system studies at a high level, like as described by the 4 science pillars. But the details of it are really critical to enable some science and facilitate some science. In some cases, facilitate some science versus some other science. So all science requirements are enhanced by the same strategy choices. So what you're referring to is the cadence optimization work, which is the work of optimizing over all the various requirements that all different science cases entail, and trying to figure out what is the best distribution of time gaps between observations in between days, right? That enables both fast transient studies as well as the study of long-term variability for secular variability for AGN, things like that. And then the other one was the parallax. So that is
Slicer.
Oh, yes. So, so the sky is. The sky looks like a sphere to us, right? You see the project. I'm taking it from a little bit far away, but the sky looks like a sphere to us. We look up at the sky, but it's all around us, and we need to project it onto a plane to put it on a slide that is a 2-dimensional object. So the heel pix is just a way in which you deproject something spherical into the plane. So heel pix is the specific kind of projection that image was based on. But what it means, what it was telling you more specifically, is how, when you simulated that image, what was the size of a unit that you were simulating, which was small, comparable and smaller than the size of the field of view of LSST in that particular case.